Okay, we were looking at this liquid flow control system. I'm making it bigger. All right. So, as I said, when we have that box on top of system, we want to see what I'm giving to the system and what I expect from the system. So, one way of looking at is to imagine that we have the assigned highest point as an input. So I'm telling what do I want to happen, and I give that to this system, and what I'm getting is that change that is happening, and I'm getting a small h from this system. Now the rate of height is proportional to the change between the difference between the capital H and a small h. So when I'm looking at rate of change of height, I'm looking at rate of change of small h. So the small h, if I have derivative of that over in respect to time, we see over the time studying such a system that is proportional, and we have a constant to fix the proportion, and that is kind of the way that we can see the system is responding. And then another study shows that from here, if we want to look at the h itself and how that one can be shown with a plot, we are looking at a plot that looks like this, and the reason is because the behavior is going to be exponential behavior. Exponential behavior. And it is reasonable because we know that at first the change is going to be noticeable, and as it goes, the water flow becomes slower and slower, and it will be saturated at some point. That's the way that we can understand the response of this system. So gradually the orange color is going to be very close to the blue line, and the blue line that you can see in this plot is going to show our the maximum value, or capital H in this case. So here the equation that we are using has a derivative, and the derivative is first order derivative. As you can see, we are looking at the rate of change. Rate of change when we are looking at first order, that is giving us a nice clue that this system is first order system. I'm going to explain another example here. We have electronic circuit, and we have one capacitor and one resistor in series with each other, and they are attached to this voltage supply. So here we are assuming that the voltage is turned on all of a sudden. So I can assume you have a switch here, and you just press the switch down, and then the current is flowing all of a sudden. So there is no gradual, anything like that. And the voltage is a value that we are giving it, and we are not changing it. So in this case, we know from previous chapter that the capacitor is going to consume some part of that voltage, and it's going to gradually charge up. So the voltage across the capacitor, we all learned that from Kirchhoff law, how to calculate that. The voltage will increase gradually and will follow that orange curve that you can see in this plot. The time, as I explained, matters. At what point of time we're looking at a system. So this transient performance, as you can see here, is going to lead the system to have that maximum value here. So we know that we can write the relationship between the voltage of, the voltage across the capacitor and the big V here, and how we can write that down as this equation here. So again, we have derivative of voltage C, Vc over time, and it is proportion with the difference between the V and Vc. And the constant here to fix the proportion is 1 over RC. And the exponential equation that can describe the system is also written here. So we can have Vc is equal to V multiplied in 1 minus e power 1t over RC. And in such a system, if we have the input given as capital V, so the output would be the Vc. This part is similar to the previous perspective of such a system. Again, the same thing applies here. We have first order derivative, so we are looking at first order system. And interestingly, the way that they are behaving are very similar. So you can see exponential behavior here and the equation that is associated with that, and also the exponential behavior here and the equation that is associated with that. So we are going to get to a generic form gradually. Now here another example is described. So we have this thermometer, and thermometer has, you can imagine it has room temperature, and then we have a liquid inside a container, and we put the thermometer inside that liquid. So we want to see how that changes, and that temperature, how we can analyze that change. We know that over some time, the temperature for the thermometer is supposed to match with the temperature that's for the liquid. That is the whole point of using thermometer, because we want to show that. So that should be exactly the same as temperature of the liquid. But how that happens, we want to look at that transient that is happening while that change is happening. So by analyzing that, it is discovered that the rate of change, here we are looking at theta. So rate at which the reading theta of thermometer changes with time is proportional to the difference between the theta, here I'm calling it theta 1 and theta h, or I'm calling it theta with no index, sorry, it's theta with no index, that is common. So when the question would be here, what is a differential equation describing how thermometer temperature changes with time? So we know that the rate of change over respect in time is proportional to that change, and there is a constant associated with that. And this is exactly what we need to get to that exponential equation that associates this system with first order systems. So if I want to plot this equation here, is going to be very similar to the one that we have here and the one that we have here. So by looking at these three examples, we are getting to a generic form. And I'm going to, I have a link that I'm describing that generic form, but before we move to that video that I have, here we are looking at different inputs that can be given to a system. So here I have a small sentence that's saying rate of change of output signal is proportional to BO theta I minus BO theta O, or better known as A1 derivative of theta O over time plus AO theta O is equal to BO theta I. So if you want to get to that generic form, again I'm explaining it by videos that I have on YouTube, but just to conclude those three examples. So here in this case, we have our exponential equation here. Here we have this exponential equation, and here we have this exponential equation. So if you want to get to a generic form, we would consider for the difference part. So for the part that I have capital H minus H, or theta, what was the one here? Theta H minus theta, or in this case capital V minus VC. So for those differences, I have this generic form. So I'm going to say that the rate of change of output signal is proportional to this change. And another way of looking at it would be from a derivative point of view. So again, if I go back here, if I want to multiply k in them, and then have an equation in a way that my theta is in one side, so it will be d theta over in respect to time plus theta is equal to k theta h. So the same applies here. If I have dvc over dt plus vc over rc is equal to v over rc. You have seen that previously in previous chapter how we simplify differential equations in a way that our inputs are all on one side of the equation, and our output is on the other side of the equation. So the same thing, when we do that with these three examples, we will end up with such a form for generic format. So here I have some constants. So A1, AO, BO, they are our constants. And in this case, I am looking at my input on the right side. So my theta I is the input function, and my output and orders of derivative of the output is in the other side. So theta O in this case is the output. And the derivative is the rate at which the output is changing with time. So for first order equations, first order derivative is present. That is the conclusion for that generic form of the equations that we can get from looking at examples. Now, getting something out of a system, that is what we expect and what we want to control. But as I mentioned, it matters what kind of input we give to that system. So here we have 4 examples of inputs that can be given to a system. So number 1 here is called a step input, and that means that for a while we have nothing, or we have 0 input, and then all of a sudden we have a constant input given to the system. So this input is very common. In this example, the thermometer was not gradually moved or coming close to the liquid. No, it was all of a sudden put inside the liquid. Or in this case, again, the voltage was given to the circuit all of a sudden by pushing a switch, or turning on voltage supply or something like that. In this case, that value that we want from the tank, that is given all of a sudden, or you can imagine the tap is open all of a sudden, so we are not gradually opening the tap, or we don't have any mechanism to control over that. So we are dealing in all 3 examples with a step input. But in some cases, we might have different types of inputs. So one different type of input can be called impulse input. An impulse input means that before that particular time, and also after that particular time, that point of time, we have nothing. We don't have any input. But in that short, sudden point of time, we have very sharp high input. Looking at examples, reviewing what we looked at them in this module, we didn't look at any impulse input closely, but I can say that in some examples that are associated with telecommunication systems, we have that impulse input, and they are useful in some fields. Another type of input that we have is called ramp input. That means that we have gradual constant increase in amount of the input. So we start from 0, but we're gradually increasing it. But the slope of it is fixed. So the rate of change of the input is fixed, is not changing with time. That is called ramp input. Now the fourth category of the input can be called sinusoidal signal. So we have oscillating signal that is moving between 2 points, maximum and minimum, and then it has this uniform shape that is oscillating constantly over the time between these points. Depends on what point at time we are looking at the input. It might have positive value, or it might have negative value, or it might actually have, we call it zero crossing, or it might cross the zero actually. So it matters what kind of input we are passing to system. We can expect the system to behave that way. And when I'm describing the videos that I have, I will also share it in the file that I have. I started to write it down here, but then I realized that it's better I actually record myself using my visualizer, as I received good comments about writing it down on paper. So I'm going to show how we solve a differential equation, and then let me check how many slides we have. I think I have a couple of recordings, and then I have some extra complementary records, and I see if I want to have a conclusion recording or not, but I think I will be done after solving the differential equation. Okay, good luck everyone. Let me